Hello everyone. Welcome to our CATIA Systems Talk. My name is Gitana Strazdowski. Our topic today is Make Embedded Software Requirements Right First Time with an end-to-end MBSE model-based system solution expert Yves GÉNEVAUX. Welcome, Yves.
Thank you very much, Ritana. Thank you to have me.
Yes, I'm really glad to have you in this CATIA talk. Today's subject is the Dassault Systems solution Stimulus that has two main functionalities: simulate and validate embedded software requirements, and automate the test to check easily if the code or the system meets its requirements. I'm sure that you will learn a lot during the session. Don't forget to ask questions. You will be able to do that during and after the presentation in the chat section. So we are ready to start, and I will start with a question. Why was the stimulus tool imagined and developed at the first place?
Thank you. Good question, Gitana. We developed the stimulus tool in a startup that was acquired 5 years ago by DS. And why did we do that? Because there was a number of studies showing that the majority of the errors which are in embedded systems are coming from wrong requirements. You see here the stat, about 56% of the errors are coming from wrong requirements. So it's a big topic, especially when you take into account the fact that the later you find the errors and the more costly it is. And requirements errors are often found during the system testing. And when you realize that the system is not behaving as expected, if you dig into the root cause of the problem, it's often a wrong requirement. So it's a big issue leading to additional costs and delays. And so there was absolutely no solution on this topic at all before stimulus.
Okay, so the figures are really impressive. But why are there so many mistakes in the requirements? What makes them so complicated to be developed correctly?
Yeah, I'm going to take a small example. Imagine a certain architecture with a number of software components here, typically. And each of these components is described in terms of behavior with a dozen, maybe two tops of informal sentences, so-called requirements, saying that when this is happening, I'm going to do this. When that is happening, I'm going to do that. So it's relationship between inputs and outputs. And you have a huge amount of these requirements written in informal text. So with a human brain, it's impossible, really impossible to figure out what's going to be the overall system behavior corresponding to all these informal statements that are supposed to apply defining the system behavior. It's actually extremely complicated, even though the guys who write them are experienced, they are educated, they can be really clever, but still a human cannot verify that and verify that there's no contradiction between two sentences in that amount of data is just a very, very difficult task. So we needed to come up with something resolving this question. So to position a bit more stimulus with the landscape of tools that you find in the development of embedded system, they can be more and more MBSE tools, so often relying on the SysML language, helping to describe the system architecture and the working principles. I say the working principles because you're not going to define all the details of the behavior with SysML. The language is not made for that. It helps you to stay at a pretty high level of abstraction, which is what you need at the beginning. But then the next tool in the chain, in general, will be something at implementation level, maybe a Simulink or equivalent, or it's directly software development. And at that level, in terms of abstraction level, you are very low. You define tons of details, you have to, which could not be described earlier. So between these two phases, there is what we call the big jump into the unknown. So starting from high-level description and going into the detail level without anything helping you in this transition is quite a challenge, to say the least. And it's true, again, when you want to test that your implementation meets the specification. If the only spec you got is a SysML model, it's probably too high. Many things are not described there for very good reasons, but then it's probably not the right artifact to verify if the implementation is correct. And we needed something in between, in the middle of this landscape.
Okay, so right. So, but what does it mean concretely to simulate software requirements? What does it look like?
So basically, if I look to the first stage, which is simulating requirements, you're going to have an architecture here in the middle. So you can capture a block diagram with the architecture and the signals. And then you will describe the detailed behavior of the blocks with requirements which look like a kind of structured English. But these requirements are executable, that they can be run, so you can observe how the system will behave once implemented. So if I say we simulate, it means you send stimuli and observe the response. If we let you do that the way you work today, in the embedded system world, it's a kind of endless process because there is so many combination of inputs that can be sent to the system that getting a proper level of confidence after your simulation, if you develop each and every test case manually, it's gonna take forever. So it doesn't work really well. Instead, in Stimulus, we define what we call a test scenario. So you basically capture a use case with the same language as for the requirements, and you can also use state machines. And these set of constraints define a space from which Stimulus will generate as many combination of inputs as you like, corresponding to that particular use case. And you will be able to execute a massive amount of simulations. So when you don't find errors anymore, then the level of confidence you have achieved is actually very high, and nothing to be compared with a couple of runs of a model like you might find in other solutions. Concretely, the interface is going to look like that. So you have here in the background the architecture you're trying to simulate. The object of interest is the blue one in the middle. We have clicked on the play button, I will show you a bit later, and define that we want one execution only here. But you could get 100 or 100,000 done automatically. And for that one, you see that the blue signal here that we have selected, which is an output of the blue block called the missile status, there is a moment where it has a completely erratic behavior. So it moves from one value to another one completely randomly, showing that for that amount of time, we are missing a constraint on this output, meaning you have found missing requirements. So that's typically one kind of errors that Stimulus is going to help you to detect. Another example here, we have the simulation that has stopped with a red vertical bar here. And if you click on the error message, it's going to show you that you have two requirements which are conflicting. One says the value shall be knock. The other one says it's going to be okay. And they are both active simultaneously. So you have obviously a conflict between these requirements. And that's, again, a solution, a result, which is very valuable. We find that a lot. There's a lot of contradictions in the requirements. And we detect that with a Stimulus through the simulation.
Wow, that's really cool. Does it mean that all the existing requirements need to be formalized into this sort of structured English? This could mean a lot of work.
I'm glad you asked, Gitana, because indeed that's a classic fear from people who discover Stimulus. And absolutely, short answer, no. You don't need to rewrite tons of existing requirements in order to be able to use Stimulus. Absolutely not. Legacy is legacy. Forget about it. And why I can say that, let me explain. So if you are creating a new function or modifying an existing one, so you have a set of requirements to be developed. And this new function interacts with the rest of the system, of course. But what you want to do is to simulate that function and have a simulation that is precise enough to find the errors in the requirements you're creating. And to have a simulation that is precise enough, you absolutely do not need to translate the thousands of requirements corresponding to the green block. Absolutely not. You just need to define a couple of constraints, which I call the stimulus stub here, to answer something that is not completely stupid when you receive an input. And that's good enough. So just a couple of constraints replace thousands and thousands of legacy requirements. It's not necessary to do anything more than that.
Okay, I get it. And then what kind of continuity is assured between CATIA Magic, the SysML modeling tool, and Stimulus?
Yeah, Dassault Systèmes, the topic digital continuity is a very important one. And we have a digital continuity between CATIA Magic and Stimulus, where CATIA Magic is focused on the architecture, as I mentioned earlier. So once you consider the architecture as mature enough, you can transfer it into Stimulus, and in Stimulus with all the signals definition. And in Stimulus, that's going to be the moment where you will create the software requirements or the detailed functional requirements. If you know a bit about CATIA Magic, in the method, we provide the magic grid, and Stimulus in that magic grid will be located here for the implementation requirements, mostly, which you capture in Stimulus and are able to simulate and validate. But you can also capture higher level requirements, system requirements, subsystem requirements, as soon as they are a relationship between inputs and outputs, and verify when you simulate the model, which is the implementation requirement, you can verify if they are aligned with the higher level requirements. And that's a verification that is extremely difficult, and that's an understatement, to do if you're just using natural language requirements.
Okay, so, and could you show us a little bit how concretely Stimulus works? Maybe you have some small live demo?
I'm glad you asked again. Yes, so going on with the same example, it's a missile, but it could be anything, an equipment of a vehicle, a medical device, whatever. So I want to simulate here this architecture and verify that the requirements I have created in the blue block, and in particular in this one, are the right ones. So how do I do that? I simply click on the play button. I can select here how many executions I want. I could get 100,000 executions, but here for the demo, I will just use one over 600 cycles. And the plotter view will display the signals I have selected because they are the ones I'm interested in. You can see the missile status here in blue, which is the output of the blue block. And after this moment where the seeker is moving from OK to knock, the value of the missile status is knock. But before this moment, as you can see here, it has a completely erratic behavior. We can zoom in. And we have here a period of time where there is no requirement producing the missile status. So you found missing requirements as I showed to you, or as I mentioned to you earlier. It's as simple as that.
Okay, so now that we have a set of properly validated software requirements, what can we do with them? Any chance to make their verification and validation activities a bit more effective?
Yes, that's only the first step, actually. the requirements, why do we create requirements? Because they're going to be the test objectives. And classically, you rewrite each and every test objective into a test case manually. And you can do much better today with Stimulus. We have made sure that the test objectives are the right ones. So now we are going to reuse the same test scenarios as before, which will generate the same test vectors, but this time we apply them on typically the code or an FMU representing the system. And we use an observer containing the requirements, which will detect automatically any violation of any requirement. And that is immensely more effective than the classic manner, because you can get a huge amount of test vectors generated from each test scenario or use case that you have identified, get a massive amount of executions, and detect automatically every violation of every requirement. This is immensely more effective than the traditional manner.
Okay, so that's really powerful. And I see that testers can perform much more tests with less effort. But what you showed to us works if the code can be compiled and run on Windows where Stimulus is installed. But you said that Stimulus is used for the development of embedded software, so there is a moment when the code is cross-compiled and runs on the real target, where the test automation you just showed us won't work anymore. Can Stimulus help once the code is running on the real hardware?
Yeah, that's also a good question, Gitana, because indeed, once the system is integrated, testing it and verifying that no requirement is violated is an extremely difficult task. And we're going to talk about it just after a quick demo of the the automated testing capability of Stimulus. So just coming back on that model, so you have done a number of executions and made sure that the set of requirements inside the blue box here, inside these two functions, are the right ones. So you have created here a piece of code implementing the missile manager. So we are just going to, in order to test that the code meets the spec, we just do drag and drop of the code here and create a second observer with the eye symbol here, within which we're going to put the validated requirements for the mission manager. And that's all what you need to do. So 10 seconds here replace probably 10 weeks in environments where you don't have Stimulus and you need to create each and every test manually derived from informal requirements. And so I just need to click on play, say, all right, make me 100 executions of the code, and please tell me if any requirement is violated at any moment for any of these executions. This is immensely more effective, again, than creating each and individual test case, running it, etc. So that's an extremely powerful way to get value out of Stimulus. It's on the right side of the V. And as you said truly, Gitana, this works while we have something that is compilable and can run on Windows where Stimulus is installed. But then you're going to use cross-compilers, embed the code onto some specific chips, maybe use real-time operating systems, and that approach won't work anymore. So in that instance, how does Stimulus help? I'll show you that now. So everybody, when you test the integrated system, capture a so-called log file containing the inputs and outputs. I can represent that with this Excel sheet. Basically, you have hundreds of columns. Each column corresponds to one signal, thousands and thousands of lines corresponding to each cycle of the clock, and tons of values. So you have an immense amount of data to be analyzed and compared to what? To thousands of informal pieces of text, which are the classic functional requirements. And that's almost impossible. So the people working in testing the integrated system work really hard on that. It's very painful, very difficult. The level of verification is sort of limited despite all their efforts and expertise. And so that's not an effective way to test the integrated system. A much more effective way is to load the log file into Stimulus so we can display the evolution of each and every input and output. You simply put into an observer the requirements, or maybe one single safety requirement, one that takes 2 minutes to write. And then you will be able to detect any violation of the observer completely automatically, instead of doing this manual analysis, which is very painful and the effectiveness of which is very limited. That's a huge, huge progress to test an integrated system.
Okay, and
I can summarize basically. Sorry, Gitana. So Stimulus, as I mentioned, is in the middle of high-level system definition with SysML and low-level system implementation, software or hardware, whatever. And it's really in the middle, helping the system engineers to refine the system requirements into software requirements first, making sure the software requirements are correct. So the guys who implement the system have a proper set of inputs to do that. And later on, when you want to test that the implementation meets its specification, the Stimulus model is the right model to do that very much automatically.
Okay, that's clear. And what do the Stimulus users say about the value they got from the tool? Do you have any quantitative results or savings you could share?
Yeah, one of the pretty impressive, at least it's a documented one. We have often very impressive results, but that one was documented and presented to the top management of this car maker. So they made a Stimulus model on a function for which defined the driving modes, you know, sports and comfort and all that stuff. In Stimulus, implemented with Simulink in that instance. And what they said first is the number of requirements was divided by 2. So it divides all the rest of the implementation by at least 2, if not more for the validation activities, maybe 4. And there was a great idea from marketing that said, oh, we have this new idea. Could you add this mode? It's called a late change in the spec, at a moment where they had something working properly already. And it happens to everybody all the time. Requirements, they change all the time, I often hear. And in that instant, instead of doing the classic impact analysis and working through tons of documents to figure out what's going to be the impact of the change, they just made the change in Stimulus. Through simulation, they were able to make sure that the spec was okay. At the beginning, it was not okay, of course, never. And then made the same in Simulink. And with the automatic testing capabilities I showed to you, they were able to converge really quickly, saying that creating a new version of a system for which you already have a Stimulus spec, the effort is actually divided by 2. They say reduced by 92%. It's enormous gain. It's absolutely enormous. And that's, I want to insist on the fact that it's a recurrent gain, because you do that all the time, working on something that exists already and improving it, making modifications, etc. So the results, as presented by this client, can be very, very strong.
Okay, so that's really, so as I said at the beginning, we will learn a lot during this presentation. So, and I believe that the audience also learned a lot through this enlightening presentation by Yves. Thanks a lot for your time being here. And let's check what questions we have on our comment section. Okay, so no, we don't have questions, which is good. I mean, the presentation was really clear. But I have one question. It's from myself actually. How how does Stimulus interact with other requirement management tools, as DOORS, for example, or others?
Yes, Stimulus is really the engineering environment for the requirements, where you produce them, you write them directly in Stimulus, you simulate, you make sure they are correct. Once you're happy with these requirements, then you can export them pretty much automatically through Excel sheets, for instance, into any requirement management tool such as DOORS. If the requirement manager is the one from Dassault Systèmes platform, we have a stronger connection, which is more powerful than simply an export or import like that.
Okay, and the other question is how long and from where to start to learn Stimulus?
How long is it to learn Stimulus? We systematically get the feedback that it was much faster to learn than tons of other modeling tools. One of the reasons is not only it's a cool tool, it's well designed, but also because the language we use is basically structured English. So you don't need to learn when, until, or greater, or until. This kind of vocabulary is the one you use already, basically. So learning how to use Stimulus is pretty short, and I have a lot of examples where we made 1 day training, and on day 2, on the second day, the client engineers themselves were writing requirements in Stimulus, performing simulation, and finding errors from the very first day they were using it operationally.
That's really great. So thanks a lot again for your time for this presentation, and thanks everyone who attended, and we will meet next month with another topic. Thanks a lot, and see you next month.
Bye-bye.